Picture this. It's 1963, and airlines across America face a problem. Their passengers want to fly between smaller cities, places like Salt Lake City, Albuquerque, Phoenix, but the economics just don't work. The jets of the era are too big, too thirsty, and demand runways longer than most regional airports can offer. The turboprops are reliable, but passengers want the speed and comfort of jet travel. Douglas Aircraft saw this gap in the market and set out to fill it with the DC-9, a twin-engine jet that would revolutionize regional air travel. The DC-9 family, including the MD-80, MD-90 and Boeing 717, remained in production for over 4 decades, from 1965 to 2006. But the path wasn't straightforward. Douglas initially explored a 4-engine design called the Model 2067 in the late 1950s, but airlines showed little interest. The message was clear. Operators wanted operational economics over raw capacity, and twin-engine configurations offered superior direct operating costs for routes under 1,000 nautical miles. Recognizing they needed to learn about rear-engine T-tail designs, Douglas signed a cooperation agreement with Sud Aviation in 1960 to market the French Caravelle in North America. The Caravelle had pioneered the rear-engine twin-jet layout, first flying in 1955. But American carriers expressed little enthusiasm for the French design. They wanted something different. A wider cabin with 5 abreast seating, indigenous manufacturer support, and performance tailored to American airports. By April 1963, Douglas committed to an all-new design. The DC-9 would feature a distinctive double-bubble fuselage cross-section, rear-mounted engines, and a T-tail configuration. Delta Airlines became the launch customer, ordering 15 aircraft plus 15 options shortly after the April 8, 1963 program approval. This partnership proved crucial. Delta gained early access to new technology, while Douglas secured the credibility needed to attract additional customers and received valuable operational feedback during development. The DC-9-10's maiden flight came on February 25, 1965. Delta received its first aircraft on December 8, 1965, just 41 weeks later, an exceptionally compressed timeline. The DC-9's defining features represented carefully calculated trade-offs. Mounting the Pratt & Whitney JT-80D engines on pylons after the wing route delivered multiple advantages. The clean wing leading edges allowed full-span slat and longer trading edge flaps without interference from engine pods, reducing takeoff and landing distances, critical for smaller airports. The design also eliminated the massive wing reinforcements needed to support underwing engine mounts, saving structural weight. These benefits came with aerodynamic challenges. The rear-mounted T-tail configuration created potential for deep stall, a dangerous condition where separated airflow blocks the tail's elevator control surfaces, making recovery impossible. The risk had been tragically demonstrated on October 22, 1963, when a BAC-111 prototype crashed during stall testing in England, killing all aboard. Douglas addressed this threat through multiple preventative measures. Stick shaker warning systems that activated well before deep stall conditions could develop, vortilons on the wing's lower leading edge that maintained airflow over the tail even at high angles of attack, and fuselage strakes that managed airflow patterns. Throughout its history, no DC-9 has ever experienced a deep stall accident. The DC-9-10 achieved takeoff capability from 5,000-foot runways through a combination of low wing loading, high lift flap systems, and the JT-80D engine's high thrust-to-weight ratio. This performance opened hundreds of secondary airports to economically viable jet service. Another defining feature was the built-in airstairs. Retractable passenger stairs integrated into the fuselage below the tail provided independent boarding capability without reliance on airport jetways, reducing infrastructure requirements and enabling operations at remote airfields. The choice of the JT-80D engine reflected strategic pragmatism. Boeing had already contracted with Pratt & Whitney to develop it for the 727 trijet. By adopting the JT-80D, Douglas leveraged existing investment, reducing development timelines and financial risk. The JT-80D's bypass ratio of 0.96 to 1.0 reflect the state of 1960s turbofan technology. While experimental high bypass designs with ratios of 5.0 to 6.0 were under development, such as the General Electric TF-39 for the C5 Galaxy, they did not enter commercial service until later in the decade. The JT-80D represented the operational standard for commercial turbofans at the time. The trade-off would become apparent years later, as next-generation engines achieved 20 to 30% fuel consumption improvements through higher bypass ratios. The DC-9's double-bubble fuselage cross-section yielded a maximum cabin width of 122.4 inches, enabling reliable 5-abreast seating. This translated to better seat-mile economics than competitors like the British BAC-111, which accommodated only 119 maximum passengers versus the DC-9 Series 50's 139 seat capacity. The Series 30 became the program's bestseller, accounting for 662 of the 976 total DC-9 aircraft, nearly 68%. This variant offered the optimal capacity-range performance balance for North American short-haul routes. The DC-9's early success, paradoxically, nearly bankrupted Douglas. By early 1967, the program faced delivery delays of 9 to 18 months. Supply chain disruptions exacerbated by Vietnam War industrial mobilization diverted critical aerospace supply capacity toward military aircraft. To secure large orders, Douglas sold early DC-9 units at a loss, with profitability deferred to later variants. Production delays cascaded into retained inventory, inflating working capital requirements. The combination of delivery delays, negative unit economics, and parallel development costs for the DC-10 created severe cash flow stress. By 1967, Douglas was less than a year from bankruptcy. McDonnell Aircraft, a defense contractor building the F-4 Phantom, sought commercial revenue diversification. The companies merged in 1967. McDonnell management brought discipline to supply chain coordination and implemented rigorous project management controls. Production schedules gradually stabilized and unit profitability improved. The DC-9's ability to operate from 5,000-foot runways enabled jet service to secondary markets. Cities including Denver, Las Vegas, and Phoenix received regular DC-9 service, where previously only turboprops were feasible. Industry analysts directly credit the DC-9 with making hub-and-spoke networks viable. Delta's Atlanta hub, American's Dallas/Fort Worth hub, and United's Denver hub relied heavily on DC-9 and later MD-80 aircraft to feed passengers into long-haul markets from secondary cities. The DC-9 family evolved through subsequent generations. The MD-80, launched in 1977, featured improved JT-80D200 engines with a 1.74 bypass ratio, delivering 12 to 15% fuel consumption reduction and Stage 3 noise compliance. Production terminated in 1999 after 1,191 aircraft were delivered. American Airlines operated 242 at its peak. The MD-90, launched in 1989, featured International Aero Engines V2500 turbofans with a 4.2 bypass ratio and glass cockpit avionics. Only 116 were delivered between 1995 and 2000. When McDonnell Douglas merged with Boeing in 1997, the MD-95 became the Boeing 717, featuring Rolls-Royce BR-715 turbofans and modern systems. Despite superior maintenance economics, only 155 were built before production ended in 2005. The DC-9's design heritage extended beyond American aviation. In 1985, Shanghai Aircraft Manufacturing Company initiated licensed co-production of the MD-80. After the joint venture collapsed around 1992, China retained manufacturing tooling. The COMAC ARJ21, launched in 2002 and first delivered in 2016, exhibits distinctive DC-9/MD-80 characteristics. Twin rear-mounted engines, a T-tail configuration, 5 abreast seating, a double-bubble fuselage, and built-in airstairs. Western analysts conclude the ARJ21 is heavily derived from MD-80 architecture. By 2025, 172 aircraft had been delivered. The DC-9 family achieved extraordinary longevity, with 2,441 aircraft produced across all variants. 976 DC-9s, 1,191 MD-80s, 116 MD-90s, and 155 Boeing 717s. Second only to the Boeing 737 among all commercial jet aircraft. The DC-9 represented a purpose-built solution to the specific challenges of short-haul jet travel in the 1960s. Its clean wing design, enabled by rear-engine architecture, short-field performance, and cabin width maximization, sustained commercial viability across 4 decades. From enabling regional network development to facilitating hub-and-spoke airline consolidation, to indirectly accelerating Boeing 737 development, the DC-9 family served over 50 years of global commercial aviation operations. Its legacy extends into the 21st century through COMAC's ARJ21, confirming the enduring relevance of Douglas's 1963 design choices to contemporary aviation development.